Hi, my name is Kian Ding and I'm going to be the instructor for this course. As you can see, in this course, we will study the mechanics of solid materials, which as the name implies is a branch of mechanics. Here are the class information. We will meet in the classroom every Tuesday, Thursdays, and the office hour will be also on Tuesday, Thursday in two different time slots. The first one is from 11:15 to 12:30, and the second is from 2:15 to 3:30 p.m. My office is located in Lerman Building, room 319. Before we start, you might want to know where this course is in the curriculum. So here is the answers. As you can see, if you are a mechanical engineering student, the course is usually taken in the fourth semester after you have studied ES201 statics. What that means is you do need to have a good understanding of statics before registering for this course. So what are the goals of this course? This course aims to provide you a basic understanding of concepts in solid materials like stress, strain, deformation, and other quantities of structures subjected to loadings. In addition, this course is also designed to help you develop problem-solving skill and to introduce you to structural design guidelines. After completing this course, I expect you to have a clear understanding of fundamental concepts of solid mechanics and basic analysis and design skills. To be more specific, after finishing this course, you will be able to number one, understand the concept of stress and strain in solid structures. Number two, understand the behavior and basic properties of materials such as yielding, elastic modulus, Poisson ratio, etc. Number three, you will be able to calculate forces, deflection, moments, stress, and strain in structural members subjected to tension, compression, torsion, bending, either separately or in combination. Number four, you will be able to understand and analyze the stability of columns. Number five, you will be able to design and predict the strength and safety of basic structural components. As to the main source of reference, we can use a textbook by Professor Hippler titled Mechanics of Materials. The one that I use is a 10th edition, which was published by Pearson in 2016. Concerning the assessment, there are three main components that I will use to determine your final grade. Though homework will account for 20%, two in-term exam, each account for 25%, and the final exam that account for 30%. In addition, I will give extra credits to those of you who frequently come to the class and who provide answers to the bonus question I or other student pose in the class. To be specific, you can be considered to have a good attendance and get 10 points of extra credit if you miss no more than 3 classes in the entire semester. Please note that there are no partial credits for this component, so you can get either 10 or 0 points. With respect to the bonus component, its count toward the final grade is conditional on your attendance record. For example, if you obtain the bonus points at the beginning of the semester and then do not maintain a good attendance, you will lose your point. Now I will use a fixed year student to illustrate to you how your final grade will be determined. Suppose this student get 90 for the homework, 105 for exam 1, 80 for exam 2, and 70 for the final exam. His aggregate grade before extra credit will be 85. Let's say he has 10 points of extra credit for his attendance. His final grade will be 95 numerically and A alphabetically. By the way, I will give you an opportunity to retake one interim exam at the end of this semester. You can choose to retake either exam 1 or exam 2. If you decide to do so, I will count the higher of the two attempts towards your final grade. As you can see in the slide, the fixed year student get 55 for his first attempt of exam 2. He later retake and get 80. I will use 80 to determine his final grade. Now I will talk about the schedule of our course. As you can see, we will have the first interim exam on the 16th of February, so please be prepared for it. Then the second interim exam will be on the 28th of March. Please note that there will be no class on the 9th of March. I will be traveling on that day. And we will use the last day of the class for the make-up and retake exams. So if you do not plan to take any of those, you can stay at home and study for the final exam. Now we will have a brief introduction of solid mechanics. As the name implies, solid mechanics is a branch of mechanics that study the behavior of solid material under external loads. More specifically, it studies the method for calculating stress and strains in structural members such as beam, columns, trusses, and shafts, etc. This course is also known under other names such as mechanics of materials, strength of materials, or deformable bodies. So why is this course important? As a civil, mechanical, or aerospace engineers, later on you will need to, number one, understand how existing structures or machines withstand the loads applied on them. Number two, understand different types of modes or mode of structure failures so that you can prevent them from happening. And number three, you will need to know how to design machines or structures so that they can withstand the intended loads while meeting other design requirements. To illustrate to you how this course is important, let us take a look at some example of structural failures in the past. The first one is the collapse of Silver Bridge on Ohio Rivers, which took place on December 15, 1967. It was the deadliest bridge disaster in the US history that killed 46 people. One thing should be noted for this disaster is before this failure, there had been no national standard for bridge inspection. The second example of structural failures was very recent, happened right here in Florida. As you may remember, a condo building in Miami suddenly collapsed on June the 24th, 2021, causing the death of 98 people. So I hope this example will provide you a strong motivation to study for this course. Next, we are going to review briefly fundamental concepts that we learned in statics. As you can see later on, these concepts are very important and will only be needed to solve solid mechanics problems. Starting with the concept of loads. By definition, loads are forces applied to a body. Based on the point of application, they can be classified into either surface or body force. As the name implies, surface loads are loads applied on the surface of an object. Based on the area or the extent of such surface, these loads can be further categorized into either concentrated loads, like this one, or distributed loads, which is spread over an area. As to the body force, it is exerted by one body to another without direct physical contact. A typical example of such force is the gravitational force, which applies on every particle composing the body. In reality, most structures are subjected to both surface and body force. However, if the weight of a structure is small, it can be assumed to be zero and be ignored in the calculation. So you should be aware of such assumption. Now let me use the above example to explain free body diagram, a very important concept in mechanics. By definition, free body diagram is a graphical illustration which is used to visualize applied force, moments, resulting reaction on a body. The free body diagram can be plotted for the entire body or for a part of a body. Usually, we will plot the free body diagram for the entire structures to find the support reactions. However, if we want to find internal loads at a specific location of the structures, we will draw free body diagram for a part of it after applying the method of section. Suppose we are interested in finding the reaction at support A and support B of these structures. The free body diagram we plot will be like this. As you can see, I plot the free body diagram for the entire beam by replacing the support at point A and at point B with support reactions. Some of you might ask why the support at A has only vertical component, while the one at B has both vertical and horizontal component. As a general rule, when we plot the reaction for any support, we will ask ourselves the following two questions. First, does the support prevent the translation of the objects in a certain direction? And second, does the support prevent the rotation of the objects about any axis? In our example, the roller support at A only prevents the vertical translation of the beam into the ground. So the only possible reaction produced by the roller at A will be vertical upward force acting on the beam. As to the pin support at B, since it prevents the translation of the beam in both horizontal and vertical direction, the reactive force can be developed at B in both directions. Because both roller and pin support do not prevent rotation, so there will be no reactive moment. By applying that rule, we can summarize the reaction for different types of supports in this table. Please note that this table is for 2D problems, meaning the body are subjected only to coplanar force system. As an example on how to use this table, if we need to draw the reaction for a fixed support, we should plot both reactive force and reactive moment. The reason is a fixed support prevents both translation and rotation of the body. Now, with the free body diagram showing all the force acting on the body, we can apply the two famous equilibrium equations to find the unknown support reaction. In statics, we learned that for stationary objects, some of the force applied to it has to be zero, and some of the moment about any point also has to be zero. Since the force and moment are vector quantities, these two expressions will correspond to 6 scalar equations for 3D and 3 equations for 2D problem. As I mentioned earlier, the ultimate goal of solid mechanics is to study the internal effects of loads exerted on a body so that we can design safe machines or structures. In order to achieve that goal, we usually use a method of section where we apply an imaginary cut through a body. And then based on the equilibrium to study internal force. While later on in this course, you will be able to find the magnitude of internal force at any location represented by each arrow here. With the equilibrium equation that you learn in statics, you will only be able to find the resultants of all this force. Such resultants are shown in this slide. It consists of resultant force and resultant moment. As you can see, they are usually placed at the centroid of the section area. Then, if we decompose the resultant force into two components, one perpendicular and one tangential to the surface, they can be called normal and shear forces, denoted by letter N and V, respectively. In the same manner, if we decompose the resultant moment vector into two components, the one perpendicular to the surface will be called torsional moment, and the other will be called bending moment. We can see that the torsional moments tend to cause the relative rotation between the top and bottom half of the body, while the bending moment tend to bend the body at the cut location. I must say that this figure is a little bit difficult to visualize for you at the moment. However, do not worry, because we will have a very clear picture later on what are normal, shear, torsion, and bending. Later, we will study each type of these internal loads separately. In the following, I'm going to discuss solution for some example statics problems. Here is the first example in which we are asked to determine the resultant internal loadings acting on the cross-section of the beam at point C. Let us analyze the problem to see how we should proceed. Based on the theory, we know that to find the internal loading at C, we should use the method of section, in which we imagine that we cut through the beam at C and then consider the equilibrium of either the left or the right segment. Let us say our initial thought is the left segment. Since there is a fixed support at A, to plot the free body diagram for such segment, we will have to replace that support by the support reaction. That means we will have to plot the free body diagram for the entire beam first, and then use the equilibrium equation to find those reactions. As such a process is quite time consuming, now we will see whether we can save some times and efforts by considering the right segment. Because there are no supports on the right segment, it is true that we can plot the free body diagram for the right segment without the need of finding support reactions. Because of that, we will now decide to proceed with the right segment. So here is the free body diagram for the right segment. As you can see, when plotting the diagram, we need to use the sign conventions for the normal force, shear force, and the bending moment. Then, to be able to find the unknown forces and moments, we will need to replace the distributed loading between C and B by a single resultant force. For that, first we need to find the intensity of the distributed loading at C and the centroid of the loading curve, which is a triangle in this case. For the former, we can base on the similar triangles to find the value of 180 Newton per meter. For the latter, we will use the table at the end of the textbook to find the centroid of a triangle. Now, it will be very easy for us to find the magnitude of the resultant force, which is equal to the area of the triangle. We are ready to apply the equilibrium equation for this free body diagram. First, based on sum of the force in horizontal direction, we can find the internal normal force at C to be 0. Then, based on sum of force in the vertical direction, we can find the internal shear force at C to be 540 Newton. Finally, based on sum of moments about point C, we can find the internal bending moment at C to be minus 1080 Newton meter. The negative side of MC simply indicates MC acts in the opposite direction to the one shown on the diagram. So we have all the answer to the question. For those of you who are curious about the first option, here is the free body diagram if we use the left segment. As I mentioned before, to plot this free body diagram, first we have to find the reaction at the fixed support at A, which are here. So what we can see from this example is we can save times by choosing the segment to be considered after sectioning through the structures. Now we will discuss the second example. In this example, we have a 500 kilogram engine which is suspended from a crane boom, and we need to determine the resultant internal loadings acting at the cross section of the beam at point E. Like the previous example, to answer that question, we need to use the method of section. Specifically, we will cut through the boom at point E and then consider the equilibrium of either the left or the right segment. If we consider the left segment, we will have to plot the free body diagram for the segment AE. As you can see, since we have a pin support at A, to plot such free body diagram, we will have to find the support reaction at point A. If we consider the right segment, we will have to plot the free body diagram for segment EB of the boom. In that case, we will have to find the force exerted by the member CD onto the boom. Based on the observation, we know that we cannot avoid the first step of finding the support reaction for this example. That means we will have to plot the free body diagram for the entire boom, regardless of whether we consider the segment AE or segment EB. Now we will discuss the solution, assuming we proceed with the left segment. Here is a free body diagram for the entire boom. As the support at A is the pin support, the reactive force can be developed in both X and Y direction. Since the member CD is a two-force member, the force exerted by it onto the boom is oriented along its direction. With this free body diagram, we can now find the reactive forces based on the equilibrium equation. Let us start with the sum of moment about point A, which help eliminate the two unknowns AX and AY in the equation. With that, we can easily find the magnitude of the force FCD. Then we can base on sum of the force in the X direction to find AX, and sum of the force in the Y direction to find AY. With those support reactions, we can now plot the free body diagram for segment AE of the boom. Let me repeat one more time that we need to follow the sign convention when plotting internal normal force, shear force, and bending moment. With the free body diagram, we can apply the equilibrium equation to find the unknown forces and moment. First, with the equilibrium of forces in horizontal direction, we can find the normal force at E. Second, with the equilibrium of forces in vertical direction, we can find the shear force at E. And finally, with the equilibrium of moments about point E, we can find the bending moment. So we provide all the answers to the question with a very simple and clear procedure. Let us continue with the next example, in which we need to find the resultant internal loadings acting on the cross section at location C of the beam. Like the previous two examples, after sectioning through the beam at C, we can either consider the equilibrium of the left or the right segment. If we use the left segment, we will have to determine the force exerted by member BC onto the beam. If we use the right segment, we will have to determine the support reaction at point A. That means in either case, we still need to find the support reaction acting on the beam. We already know that to find the reaction, we should plot the free body diagram for the entire beam. Noticing that member BD is a two-force member. Now, assuming we decided to use the left segment of the beam to find the internal loadings at C, we will then use this free body diagram to find the force FBD. As you can see, that force can be found by taking sum of moment about point A. Here is that summation, from which we can find the force FBD to be 360 pounds. With that, we will plot the free body diagram for the left segment of the beam, which is shown here. From the free body diagram, we will apply the equilibrium equation to find the internal loadings at C. First, from the equilibrium of forces in horizontal direction, we can find the internal normal force. Second, from the equilibrium of forces in vertical direction, we can find the shear force. And finally, we can use the sum of moments about point C to find the bending moment. Those are the three examples that we use to help you review statics. With this example, I hope you will have a clear picture on the procedure to solve a typical statics problem. Thank you and see you in the next lectures.